Hello and welcome to the third part of this section 2.2, the derivative as a function. To continue on, we have this example here, example 4. If f of x is equal to x cubed minus x, we want to find and interpret f prime of x and f double prime of x. So, to find these particular values, let me do a part of this work up here for right now. To get that value of f of x plus h minus f of x divided by h based upon our function, this is going to be x plus h cubed minus x plus h minus x cubed minus x, all divided by h. So we need to expand that out a bit, which is why I'm doing this up here. Expanding out this x plus h cubed, this makes x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h minus x cubed plus x, all divided by h. So a few of these easily cancel out, right? We are left with 3x squared h plus 3xh squared plus h cubed minus h, all divided by h. And lastly, that cancels out a bit, just to leave us 3x squared plus 3xh plus h squared minus 1. So, for the f prime of x, being that limit as h approaches 0 of this f of x plus h minus f of x divided by h, we can, well, let me write that step first, actually. This is of x plus h cubed minus x plus h minus x cubed minus x, all divided by h. This amounts to, just nicely, the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 1, and that makes, nicely, 3x squared minus 1. For that second derivative of x, we are going to have the limit as h approaches 0. This would be, now using the derivative, 3 times x plus h squared minus 1 minus 3x squared minus 1, all divided by h. So, to find this one now, we need to expand this. So this would be the limit as h approaches 0 of, this would be 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1, all divided by h. So again, few things cancel. Limit as h approaches 0 of, and yeah, of this will be 3. So a couple of things cancel out here, which would be nice. We are left with 6xh plus 3h squared and that will be divided by h, which gives us the limit as h approaches 0 of 6x plus 3h, which just gives us 6x when we put in 0 for h. So the acceleration. In general, the second derivative is interpreted as a rate of change of a rate of change. So if we have s is equal to s of t being our position function of an object that moves in a straight line, the first derivative is the velocity v of t of the object as a function of time. So v of t is equal to s prime of t, which is ds over dt. The derivative of the velocity function, which is the second derivative of the position function, is the acceleration function. So a of t would be equal to v prime of t, which is the second derivative of s of t. Or in Leibniz notation, a is dv over dt, or d squared s over dt squared. The third derivative, to go even higher, f triple prime, is the derivative of the second derivative. So f triple prime is the second derivative prime, and f triple prime of x can be interpreted as the slope of the curve y is equal to f double prime of x, or as the rate of change of f double prime of x. In Leibniz notation, this is expressed as y triple prime is equal to f triple prime of f of x is equal to d over dx of d squared y over dx squared. So that being d cubed y over dx cubed. And we can interpret now that third derivative of our position function s. So s triple prime being equal to the s double prime prime is equal to a prime. The third derivative of the position function is the derivative of the acceleration function, and this is called the jerk of the motion. The jerk is the rate of change of acceleration. So a large jerk is a sudden change in acceleration, which causes an abrupt movement or that jerking around, such as like with the car, if you jerk one direction while trying to change lanes or something. In Leibniz notation, J would be dA over dt, which will be d cubed s over dt cubed. So this is the third part of section 2.2 on that derivative as a function. Be on the lookout for the fourth part. Thank you.